Okay, as the title of today's lecture implies, we'll be discussing outliers, how you find them, what you do about them, and so forth. I guess, well, two quick announcements before I go into that. Number one, we have a room for the discussion section now. It's, I believe, G502 in Curry. Curry is the new dental school building just across the street. And the other announcement is homework one is due on Friday. I mean, as I said, I try not to be too big of an ogre on due dates. If you turn it in by the due date, you'll get a small bonus. If you can't, don't worry about it, but do try to get it in within a week of the due date, just so we can get it graded and solutions posted in a similar manner. At any rate, outliers. As you'll recall, we've discussed before, and you probably know the terminology already. An outlier is kind of an extreme value in a data set, an unusually large or small value, and quite often it's the result of bad data that either your equipment malfunctioned or somebody miskeyed the data when they were entering it into the computer, whatever the case may be. And if there's bad data in your data set and you don't do anything about it, that can lead to problems. Two of the most common summary statistics that people calculate are means and standard deviations, neither of which are resistant to outliers. You put a single bad data point in your data set and you can get all kinds of screwy results. On the other hand, if you get rid of data that you think is bad but actually isn't bad, that can also throw things off. And I mean, you get this. I mean, there's some famous disasters in this area, as I've talked about before in the stock market, that people assume that, oh, the event where everybody stops paying their subprime mortgages at once is so rare that it would never happen in real life, and yeah, then suddenly you end up just wrecking the economy. So, you don't want to throw out data that you think's bad when it's actually not bad. Oh, just to give an illustration of the process that you might go through to detect outliers, there's a data set built into R that's a fairly famous data set in the history of science called the Michelson-Morley experiment. If you're a history of science buff, you might know something about this, that in the 19th century, they believed the light waves were like sound waves. They had to pass through some kind of physical medium that was called luminiferous ether. And the idea was the Earth and the Sun are both moving through this ether, so you should be able to observe what they postulated was an ether wind, that if light is going the same direction as the Earth or the Sun, then the speed of light should be slightly greater, or if it's going in the opposite direction, it should be slightly less. So Michelson and Morley were trying to measure the speed of this ether wind by measuring the speed of light very precisely in a number of different directions and hoping that it would be slightly different depending on the direction that they measured it. And basically, the experiment failed, ultimately leading to Einstein's theory of relativity. This is one of those famous examples in history of when an experiment failed and gave the results they didn't wanted and still produced something good. But for the purpose of today, we're mainly interested in searching this data for outliers, that if you're going to report results that are going to it's going to force the world to completely rethink the fundamental theories of physics, you want to make sure that these results aren't due to weird data. So, a common rule of thumb for detecting outliers is that an observation that's more than 1.5 IQR's 1.5 interquartile range is above the third quantile or below the first quantile is a possible outlier. I'll recall the interquartile range is the difference between the third quartile and the first quartile. And should be pointed out, this is just a rule of thumb to help you start looking around for suspicious data points. This is not hard and fast gospel. And I try to emphasize this every year, but every year I have somebody on the homework who goes through and just says, well, this data point is slightly more than 1.5 IQRs outside above the third quartile, we should get rid of it. It's no bad. Just because an observation is a bit extreme doesn't mean that you should get rid of it. So I'll show you a couple examples later in today's lecture of perfectly valid data points that violate this criteria. Even perfectly valid data points that violate this criteria, in which case you would not want to remove those. The purpose of this rule is mainly to just help you flag suspicious data points, to be able to say, okay, maybe I should go double check my code book on this one, make sure there's nothing wrong with that particular data point. So, really simple example of this. Hey, you have a data set consisting of these 5 data points. Since you only have 5 data points, it's easy to calculate that the median is 83, the first quartile is 70, the third quartile is 92. So the interquartile range would be 92 minus 70, which is 22. So you take the third quartile plus 1.5 times 22, which is 125, or you also take the first quartile minus 1.5 times 22, which is 37. There's no data points outside of that range in either direction, so you don't see any putative outliers in this data set. Practice, of course, you probably wouldn't want to do is when you only have 5 data points. It's just kind of an illustration to show you how this would be done just so you understand kind of what we're doing here. And if you really wanted to do that in R, here's the R commands to do it. Recall in R, if you give it the sort command, it will sort a data set from smallest to largest. And if you give it the quantile command, it will give you the 0, 25, 50, 75, and 100% quantiles for distribution by default. You can tell it, you can specify other quantiles if you want it, but for today, this just shows how you can take third quantile plus 1.5 times the IQR, first quartile minus 1.5 times the IQR.
Just a quick R question. So if you type out quantile, can you give that a new variable name, like a la MATLAB, and then reference the second and the third entries in order to get, instead of typing in the 70 and 92? Yeah?
Yes, the question was, can you use the quantile, sort of save the output of the quantile command in another variable, and then just reference that variable rather than writing out the variables I did on this slide. And yes, you can do that, and I guess I'll just write the syntax on the board, and I apologize to those who are watching on YouTube that you won't be able to see this, but you could do something like define a variable test.q equals quantile test, and then test.q will be a vector of length 5 in this case, where the 0% quantile is the first element, the 25% quantile is the second element, and so on. Instead of writing these numbers out manually, you could then say test.q square brackets 3, the third element of this vector, which would in this case be 83, plus 1.5 times test.q of 4 minus like that. Those watching on YouTube, you didn't miss anything super critical. That's just giving some information about R if you ever need to do a trick like that in the homework. If I'm not going to ask you to do anything particularly sophisticated in this class very often. If I do, you're always welcome to email me if you run into issues, or email Eric, or whatever the case may be. Oh, in the Michelson-Morley experiment, this data set is built into R. It's called Morley. So once again, if you say attach Morley, you can reference the columns of the data set. So I can just say sort speed rather than sort Morley $speed. And see, the median of this data set in this case is 850. The 25% and 75% quantiles are 807.5 and 892.5. So once again, you can use this criterion and say 892.5 plus 1.5 times the interquartile range, we get an upper limit of 1020 and a lower limit of 680. And as you can see here, I marked the potential outliers in red, that you have 2 observations below this 1.5 times IQR criteria and 1 observation above it. Oh, if you were mindlessly applying the criteria, those would be the data points that you would want to check to see if there's something wrong with them. Now, in practice, you will almost never actually calculate these quartiles and crank through the math like this. In practice, people normally use box plots just because it's much quicker and easier. Do a box plot of the Michelson-Morley data. If you'll recall from Monday's lecture, by convention in the box plot, the top of the box is the 75% quantile, the bottom of the box is the 25% quantile, and the whiskers on the box go to the most extreme observation that's within 1.5 IQRs of the third quartile or the first quartile, as the case may be. So in this case, we see 1 dot at the top, 2 dots at the bottom. Those correspond to the 3 data points that I flagged on the previous slide as being outside the range according to that criteria that you may want to check to see if those data points are actually valid. So there's other criteria that are sometimes used for detecting outliers. Sometimes people will do 3 standard deviations from the mean or something like that. In general, the IQR-based criteria is more commonly used and probably better in my opinion, just because it said medians and interquartile ranges are robust against outliers, whereas means and standard deviations are not. So if you have a really bad outlier and you use the criteria based on the standard deviation, it may not look like that bad of an outlier, just because the fact that it's an outlier made your standard deviation very large. But that's sort of beside the point. More important here is that these rules are just intended to help you find suspicious data points. They're not intended to be gospel, and you have to use common sense. If you can even have data points that are within 1.5 IQRs of the various quartiles and still be invalid if they're physically impossible. I mean, if the variable is the weight of a mouse in your lab in kilograms and one of them is negative, well, It may be that all the numbers are so close to zero that when you calculate when you try to calculate according to these criteria, that it looks like it's this negative value is within 1.5 IQRs of the first quartile. That's obviously still an invalid data point. So don't let these rules try to substitute for common sense. You'll have to just look at the data and say, okay, is there anything out of range? How big or how small would I expect it to be? Things like that. So the big question when you identify suspicious data is, should you get rid of it? If, as I said before, if you keep erroneous data in your data set, you can get invalid results, particularly for things like mean and standard deviations. But if you toss good data, that can also mess things up. So when do you get rid of it? This is where it's really a judgment call, and it's as much of an art as a science. I can't give you a list of rules that tell you what to do in every situation, but I can give some general guidelines. So the first thing that you should check is out of range values, physically impossible values. If a number is out of range or physically impossible, get rid of it. That's an absolute no-brainer. If the variable is weight or height or age or something, one of the numbers is negative, that's clearly wrong. Or if, for example, you're measuring someone, if the variable is someone's heart rate and the heart rate, and you have a heart rate of like 2 or a heart rate of 2,000 or something like that, you're going to say, okay, anybody with a heart rate that low or that high is probably going to be dead. That number is going to be wrong. Those are the easy ones. In practice, most of the time, it's not going to be that easy. Another one that's fairly easy is if you can verify that there was some sort of mistake in data collection, that if you were using some type of machine to collect the data, and you look at the log and it says that it was malfunctioning that day, okay, that's a good sign that it's a bad data point. Or if you go and look at the lab notebook and you find an annotation there that says, I miskeyed this into the database, it wouldn't let me change it after I keyed it in, okay, then once again you know that it's wrong. And I mean, the other rule of thumb that you can use, if there's a really huge gap between your outlier and the rest of the data, it's more likely to be spurious. Even that's not a perfect rule, but the idea is if all your data is clumped together and there's a huge gap and one data point way at the end, that's more likely to be bad than if you just see a data set that looks skewed. I'll give some examples of this here in a minute, where you see bunches of data that are all outside the usual range. And another thing that you can look at is for batch effects, that if you see several suspicious values that were all collected the same day or time, or collected by the same experiment or the same instrument or whatever the case may be, then there's a greater likelihood there was something wrong with the equipment that particular day or something wrong with the person collecting the data or whatever. But, I mean, once again, if I haven't beaten this horse to death already, none of these are the be-all, end-all. You just have to use good judgment and common sense. And most of the rest of today's lecture, I'm just going to describe a couple case studies of when you might want to or not want to get rid of outliers. So, the Michelson-Morley data, in this case, we don't have like their original lab notebooks or anything like that. So how can we know if these suspicious data values are quote-unquote real? Well, in this particular data set, they collected it in a series of 5 different batches. So let's plot side-by-side box plots for each batch individually. And we see here that the value of 1070 that had been flagged as suspicious looks a bit less suspicious when we look at it by batch. It clearly came from batch 1. That's the highest value in the data set. In batch 1, we see, first of all, it had larger variability than any of the other batches, and also was a little bit higher on average than the other batches for whatever reason. So the fact that the largest observation in the data set happened to be in batch 1, we become less worried about that particular data point. And one of the outliers on the low end was in that particular batch as well, but again, this is the batch with the greatest variance, so won't necessarily have a huge amount of heartburn. Batch 3 is the more interesting one because for the most part, they were all clumped very close together as evidenced by this box plot, but then there's 4 data points all outside the range. In particular, the lowest observation in the data set, the one that we had flagged as suspicious earlier, was also in this batch. And I mean, in this case, was there something wrong with that measurement? Should they have gotten rid of that data point? Quite honestly, it beats me. Without knowing more about the details, their data collection procedure or limitations of their data collection, I really can't say whether or not that should be removed. Luckily, it's probably not going to make a big difference in the analysis one way or another. However, what I can say is that if if I were told that one data point is bad and I had to guess which one it was, that one probably looks more suspicious than any of the others. So, yeah, most of the stuff on this slide, I just said that we're less worried about 1070 because it was in batch 1 that had higher variance and higher values overall. 650 was also in batch 1, but that one had higher variance. It was the 620 that was in batch 3 that we're the most worried about, but I mean, even then, like I say, it's tentative. We can't really know for sure. And just for reference, here's the commands in R that I use to generate these plots. To get the box plot for the full data set, I just said box plot speed, and then I put a header and a y-axis label, and then I also did it by batch when I said speed, twiddle, experiment. Remember, I attached the Morley data frame earlier so I could reference the columns in the data frame, namely speed and experiment, without needing to use Morley $ experiment or whatever the case may be. So, another example of outlier detection / removal. This comes from a data set that I worked on myself with a doctor in the medical school who was trying to develop a new device that could be used to develop a clinical diagnostic test for pelvic pain. And basically, my collaborator in the medical school just palpated the patient in several different locations and measured how much pressure the patient could tolerate. And the long-term objective of this study is to predict the patient's tolerance to the pain or how much pressure they can endure based on the site of the examination and whether or not the patient has the chronic pain condition of interest. So basically, we build a model to try to predict a patient's tolerance to pain based on the examination site and whether or not they have the chronic pain condition. And for the most part, the model worked pretty well. But just given site plus whether or not they had the condition, we could predict their pain tolerance with quite a bit of accuracy. But there were a number of big outliers, and that raised the question, was there something wrong with these particular measurements, or would they fall within the range of what we would expect? So we did a box plot of the error in the model, and as you can see, it had an extremely long right tail that for the vast majority of the patients, the error in our model was practically zero, but for some relatively small subsets, we were off more, in some cases off quite badly. So that raised the question, why are some of these observations so far out there? So we tried to look at this a little bit more closely to figure out what was going on. And here's a histogram of the errors in the model, and you can see the same thing, that 1,500 measurements were all close to zero, but some small number went all the way out to 15. It's like, okay, that's weird. Why are some of these errors so large? Oh, the best way to do this would be you just plot the error for each patient one at a time and see if some patients showed higher error than others. Again, this is like if you can partition your data into subgroups, that may help you identify the problem. If you just see unusually high errors scattered throughout your data set, maybe that's just noise that you can't do anything about. But if it's the same patient that's way off every single time, that suggests there was something weird with that patient or with your data collection procedure that day or something. But we had over 100 patients in the study. We didn't want to generate graphs and look at graphs for every single one of them. So what we did is we plotted the error against the predicted tolerance, since our thinking was that similar data points from the same study site and the same pain condition status should have similar predicted tolerance. And the plot looked like this, and what you notice here is that the unusually large values all have the same predicted values. So the fact that the predicted value is the same suggests that the extreme observations probably all came from the same person. So you're like, okay, let's go through our data, try to find people who systematically have a bunch of unusually high measurements, and let's see what we can figure out with those particular people. So we went through our data set and discovered indeed that almost all of the extreme values in the data set came from 4 different patients. Said, okay, now we've narrowed down the problem to these 4 patients. Let's pull the charts for these 4 patients and see if we can figure out any reason why their data might be weird. Well, for one of the suspicious patients, the chart said that one day that we collected the data, it said that we got a warning that our machine was out of calibration and the numbers may be bad. It's like, okay, bad data. We can drop that patient. The other patient, we couldn't see anything wrong in the chart, but it was saying that the examiner was exerting something like 20 newtons of force using this little device, and we knew perfectly well our examiner wasn't strong enough to exert more than like 5 newtons of force. So we're just like, okay, not sure how that 15 got into the database, but it's wrong, we can drop that. The other 2 patients, we couldn't find any reason that they would have unusual measurements. As it turned out, the 2 that we got rid of were the 2 that had the largest sets of errors. The other 2, even though their errors were unusually large, they were smaller compared to the 2 that we did get rid of. So we said, okay, we'll keep those 2 in the data set. because generally speaking, when you're doing this outlier detection procedure, you're better off erring on the side of keeping too much data rather than throwing out good data, because you throw out good data and it starts to bias your results, whereas keeping bad data, especially if your sample size is large enough, the error tends to average itself out anyway. Now I'll illustrate a couple examples where if one were to just mindlessly apply the 1.5 times IQR procedure, that you could get yourself into trouble. This data is another data set that's built into R that records the closing price of France's CAC stock market index every day from 1991 to 1998. There's a total of 1,860 observations. And so let's say we want to check for outliers in this data set, so we draw a box plot. We draw a box plot and it looks like this, and if you're just naively applying the rule, you might think, holy cow, we've got 10 bazillion outliers right here. This whole bunch of numbers above the 1.5 times third quartile. We need to get rid of a lot of this data. Well, the first thing that should jump to mind is the warning I gave earlier, that if you plot the box plot and there's a big clump of points down at the bottom, then a single point way up at the top, that's really likely to be bad. Whereas if you see something like this, that's more of just like a skewed data set. It doesn't necessarily indicate that all these data points are weird. In fact, if we look at the distribution of the data more closely, we'll see that having this really long tail actually isn't that surprising. This is a plot of the closing values of the CAC index over time. As you'll recall, in the late 90s, we had a stock market bubble, even though for the vast majority of the decade, the index remained in approximately the same range. Suddenly, beginning about 1996, it just took off for the sky. Well, compared to the first several years of data, pretty much all of these data points were outliers, but they don't represent valid data. Are the actual values of the stock market index. It's just they appeared unusually high because the stock market suddenly went much higher than it would normally go based on historical norms. Oh, yeah. I guess I already said most of this. The main take-home message is that just because you see unusually large values on your box plot, that doesn't mean that it's garbage data that needs to be removed. You should plot the data in a couple other different ways and also try to use common sense. And just for the sake of curiosity, if you want the R commands to reproduce this plot, this data comes from another data set that's built into R that's called EU stock markets. There are several columns in this data set, each of which has the stock indices for a particular European country. In this case, I'm looking at the third column of this particular data frame, which is the French CAC index. Come to think, but I don't think I've introduced this notation before. In R, if you have a data frame, basically that's something that has both rows and columns. It's like a spreadsheet. In this case, the columns represent the indices for different stock markets, and the rows represent a day's worth of data. When you see this notation here, EU stock market square brackets, comma, 3, that says take the third column of this particular data frame, i.e. the CAC index column. If I had said EU stock markets square brackets 5, comma 3, that would say take the fifth row and the third column. since I don't specify an index for the row, it takes every single one of the rows in that column. So basically, it just gives you the third column of that particular database, or that particular data frame, or that particular spreadsheet, as the case may be. And if you want to do the time series plot of this data set, the command is just called plot. Once again, I do the square brackets 3, give it a y label, and graph header. As I said, EU stock market square brackets 3, that gives you the third column of the EU stock markets matrix, or I think it's technically a data frame. And the plot command is a very general command that you can use to plot all kinds of things. We'll use it for a couple other things later in this class. In this case, it recognizes this data frame as a time series and gives you a time series plot. You don't need to worry about those details for now. In fact, in this class, we are never going to look at time series again unless one of you is looking at time series in your lab and wants me to discuss it later in this class for some reason. I mean, otherwise, this is just for academic interest. How did it know to do the plot like it did on the other slide? It's because the plot command in R is smart. And another example of when just mindlessly getting rid of outliers could get you into trouble is another data set in R that records the number of sunspots observed every month from 1749, between 1749 and 1997. There's a total of just under 3,000 such observations. Let's say that we want to check for outliers in this data set. So we do the box plot, and once again, we see a bunch of things above 1.5 to IQRs above the third quartile. And I mean, just looking at the box plot, hopefully you can already see that the issue here might be skewness rather than bad data. Notice the whisker down at the bottom is really short, but the whisker up at the top is very long. That's indicative of a skewed data set, indicating that there's a law that the data points above the 75% quantile get large fast. And then once again, you need to see a couple of points that kind of stick out a little, but for the most part, the points are pretty clumped together, again, indicative of skewness rather than having one or two single points that are way above everything else. Oh, but let's say we want to try to figure out if these extreme values measurement errors or legitimate data. Well, let's draw a histogram and see what the distribution of this data looks like. And this histogram confirms that there's some extreme right skewness in this data set. The vast majority of months, there are very few sunspots, but every so often you'll have a rare month where there's a much higher number of sunspots. It's not like we're seeing negative values or a number in the millions, something that's clearly out of range. It looks like a surprisingly orderly distribution of the data, that the number of sunspots decreases steadily, or the count, I didn't sleep enough last night. The counts decrease steadily as the number of sunspots increases, but nothing that particularly jumps out at you as something that's clearly wrong. So, the basic conclusion is that it's rare to see larger number of sunspots in a month, but it does happen. So these outliers in the sunspot data set most likely represent valid data. In fact, I would say almost certainly represent valid data in this case. And once again, if you want the R commands to create these graphs, basically the same thing that we discussed earlier, just go box plot sunspot.month or hist sunspot.month. This sunspot.month data set is also built into R that contains this list of sunspots that I just gave you. So, important things to remember for today is that outliers are extreme values in a data set that could possibly represent bad data, and the most common way to detect them is you draw a box plot or you look at the IQR of the data, but these are just general guidelines, they're not foolproof. And if you find a putative outlier, you have to try to determine whether or not it's real and remove it if you think it's wrong. And more often than not, this is a judgment call. And for the purposes of this class, and for the purposes of using applied statistics in real life when you're writing papers and so forth, oftentimes the really crucial thing is just that you can justify whatever decision that you made, or particularly if you remove data, it needs to be well justified that I removed this data point because it was outside the range and I checked my lab notebook and the machine wasn't working correctly that day. Or, I mean, if you plot your data and see something unusual, said, we decided not to get rid of this data point because there was no indication that it represented bad data. A lot of science just boils down to being able to write a few sentences or a paragraph defending the decision that you made. And even though you could make a case for doing it either way, and yeah, then you just send it off to the journal and hope the reviewers don't vehemently disagree, in which case you change it. That's life, I guess.